bolt. They let me sit in it, but they wouldn't let me drive it.
No.
And that was before they did the whole recall, the full recall thing. So
All right. So we have much of our crew here.
You're muted, Scott.
Oh, hang on. There we go. Now you can hear me?
Yeah.
Okay. I'm just I'm adjusting my television set, as it were. Remember those old statements? Please do not adjust your television set. Well, I have to.
And you get to the horizontal hold and the vertical hold, and then the
Right.
picture brightness. Mm-hmm.
I had forgotten about that.
And then you have to adjust the ears.
Yeah.
You get your aluminum foil and
Yeah.
And the old RF modulator.
Well, welcome those of you who are viewing us online. This is Sidewalk Science. You'll pardon me if I'm occasionally a slightly bit distracted. I'm sort of running the technology today as well as participating. We're coming to you courtesy of the Prairie State Humanists. You can find us on meetup.com if you do a search for Prairie State Humanists. And we're a chapter of the American Humanist Association. We happen to be based out of the western suburbs of Chicago, but most of our programs are accessible online. And we welcome your participation and as active as you would like that participation to be. So hopefully you can see on the YouTube channel that there's an area where you can enter chats. So you can type in questions and comments as we go through our program today. And I will do my best to get to them and make sure that we address your questions and comments. So without further ado, we've got a 3-part program, as is typical. We're going to start with a little bit of science news, and then we're going to have a deep dive topic today. Joanne will be doing our deep dive, and she's going to shed light on the universe, as it were.
as it were.
There's going to be a lot of illuminating metaphors today. I make this prediction. A couple of interesting pieces of science news that I've seen recently. One was a star that has been discovered that seems to have been ejected by the core black hole of our galaxy. And it's traveling about 1,800 kilometers per second. So what is that? Is that about 10% the speed of light?
Really quick.
No, that's
1%.
That would be like, well, half a percent. 0.6%, something like that.
Oh, that's right. I was getting miles and kilometers mixed up. It's 100. It's 300,000. Okay.
The headlines have been a bit misleading. Certainly, the object seems to track back to the central black hole, but there's no real mechanism by which the black hole itself, by itself, could have ejected this object. On the other hand, in that central region of the galaxy, there's a lot of stuff whizzing around at very high speed. And if you have a close encounter between two stars, one of them could be ejected while the other one becomes more tightly bound, or it could have been part of a binary where its companion went supernova and disappeared. And it tracks back to the central black hole, but I think that's an indication that there's just a lot of stuff there. And if you're going to have a high velocity star, that's a likely place for it to start.
It's kind of a mosh pit in the center of our galaxy.
Yeah, it's quite crazy to look at. It's hard to see in the visible, but you look at it in the infrared or in the X-ray, and it's really complicated down there.
Yeah.
It's nice to be way out here in the suburbs.
Yes.
The other, another piece of what I just chose randomly as an interesting piece of science news was the whitest paint ever. So apparently this paint reflects 98% of the incident white light, and it radiates infrared light, more infrared light than it absorbs in the visible spectrum, so it can actually actively cool off a building that is painted with this paint. Sort of a passive radiative air conditioning. I don't know.
I was thinking to myself, is this good or is this bad? That we have buildings that are going to actually heat up the atmosphere all by themselves.
Well, they do that anyway.
Yeah, it's work.
This is going to be even better.
But it's actually better because instead of pumping the heat out, which generates more heat,
From an air conditioner.
Are just radiating the heat out. Yeah, we have materials we use on spacecraft for that kind of thing. There's a common thing that we use is called silver Teflon, where you have a silver backed Teflon tape. And the Teflon's transparent to light, but the silver is really reflective. On the other hand, the Teflon radiates infrared very well. And yes, you can put that stuff in direct sunlight and it gets cold.
That's amazing.
Well, has anybody talked about the magnets at MIT yet?
No.
Oh, this came out actually over a week ago. But basically, the people who are working on fusion at MIT announced that they had managed to come up with some new superconducting magnets that are of record strength. And this means that, well, one obstacle towards fusion has been dealt with. And they're very excited about this.
And the great thing about a superconducting magnet is that it doesn't use a lot of electricity. Way back when I was an undergraduate, I worked over there. And we used to have to call up the electric company when we turned on the more powerful magnets in the building because they had to put extra capacity online.
Yeah, I would say that is a more socially responsible use of a great deal of electricity than some of the stories I've been seeing recently about the amount of electricity globally being used by cryptocurrency miners. Something like the entire electricity budget of Argentina globally is being used or consumed and being turned into heat and other sorts of pollution from the electricity generation, potentially, just by cryptocurrency mining.
Well, getting back to the fusion, the whole idea behind fusion is that if we can actually manage to do this, then we get lots of carbon-free electricity. And I mean, it's the kind of thing where we're always hearing that, you know, fusion is 30 years in the future, and it keeps being that way.
Yeah.
But in this case, they've kind of moved it up to 10 years in the future.
Wow.
So this seems like some kind of progress. I'm just going to get exactly what they told us here. They are saying that
they're very optimistic over there. I used to work over there.
They always are. As I said, you know, it's always 30 years in the future, but now it's less than 10 years in the future. It says they hope to have a demonstration device, that is to say fusion device, by 2025, which is not very long. The nice thing about them sticking their necks out like that is that that's actually a short enough amount of time that we can check up on them in a few years and see if they made it or not.
Yeah. Rather than
It's
30
a
years
long
and 30
road,
years.
though.
Right. Rather than 30 years and 30 years, and it's always kind of a rolling 30 years. This is actually something that, if they're making that kind of number, you think that maybe they have some idea that they have a plan.
They might be onto something.
Well, it's a long road from a demonstration device to a power plant, though.
Oh, sure.
There are a bunch of unsolved problems. The easy to ignite fuels tend to make lots of neutrons when they fuse, and that's both bad because it's good because the neutrons go out through the vessel and you can capture them outside, which is good. The bad thing is they go through the vessel and they damage the vessel. Yeah, it's the engineering that would take a demonstration device into an actual power plant is quite difficult and not completely solved.
Well, there are always problems in engineering, but at least in this case, if they can get a demonstration device up, the whole idea of proof of concept is actually pretty cool.
It does help.
Yeah, it helps.
Yeah, and there's lots and lots, I haven't heard much about the Stellarator in a year or so, and that's my favorite fusion enabling technology, just because it's got the coolest name on the planet, in my opinion.
Mm-hmm. Where's that?
Yeah, I think it's in the European Union, maybe being built somewhere.
There's a new, of course, the Stellarator idea was invented around the time I was born in Princeton. So it's been
the dinosaurs, huh?
Yeah, well, it's been around
30 years.
It's been around for a long time. The new thing is that this group in Germany claims they've done supercomputer simulations, and they figured out how to create a ridiculously tangled magnetic field that will suppress all the magnetic field instabilities.
Yeah.
Which has always been the problem with stellarators. And the problem is that the history is that every time somebody figures out, oh, we know how to suppress the instabilities, the plasma figures out a way to make a new kind of instability.
There was one more science news issue I wanted to bring up. That's, we talk about being the intersection of science and humanism on this program, and we tend to focus a lot on the science and not as often on the humanism. But there was a recent study about people's perception of good and evil and their perception of the supernatural, demons and angels and gods and whatnot. And if I read the story correctly, one of the implications of that was that people perceive evil entities, whether they're evil human beings or imaginary evil things, as being predominantly selfish and either unable or unwilling to consider the ramifications of their actions on others. So I'm using my own term. This wasn't in the articles I read, but it sounds to me like sociopathic. So they sort of identify evil with a sociopathic tendency. And this is universal, whether they're thinking about an evil spirit or god or demon, associated with a religious myth, or whether they're thinking about people that they consider evil. And then on the other hand, people they consider benevolent or good are people that they think take into account in a much deeper way the implications of their actions on others. So I thought that was interesting, and I wonder if there's relationships between that and the invective political divides we have that sometimes separate good people from other good people. Just sort of an open philosophical pondering. All right.
I did see another survey that said that I think for the first time, more than 50% of Americans believe in the theory of evolution.
Yeah.
For the first time.
Yeah, we're making some progress there.
Yeah. But ever more.
There was another one that came out that they looked at very large numbers of people to find out why people were so excited about these conspiracy myths and what it was that drove this and what was going on. And it appeared, based upon these studies, and there was 5 or 6 of them, fairly large, that it's more exciting. Not that there's any greater truth, but one is an exciting story and the other isn't. And it's all filled with mystery and magic and everything else. And this makes for a wonderful novel. And so people are attracted towards this marvelous thing rather than the dull, dry, this is how it is, look. So again, the people's imagination drives them much more than our logic systems. And isn't that always the way? Our emotions carry us away, and sooner or later our thought processes try to catch up, but don't.
Yeah, good insights there. And maybe
It happens in science too. I remember when I was a grad student, I was working on spacecraft ops, and the professor I was working for always wanted to do the operation in the most exciting possible way. And I had to kind of try and calm him down because the most exciting possible way wasn't always the best way to do the operation.
yeah, it might end in too many explosions.
Well,
Chemistry lab, yeah, it goes bang.
yeah, it wasn't that bad, but it was just, oh, you could waste a day pointing in the wrong place or something like that, you know. And, you know, when you're spending $100,000 a day, that's kind of a big deal, right?
Yeah, for sure.
All right. Well, maybe in the future, you know, I'll try, as I think of and discover science news stories, I'll try to continue to find at least one story that talks about, you know, belief or a social issue or something that is more in tune with some of the activities and focuses of the humanist organizations that we all are members of, in addition to pure science.
You did see that Pew recently came out with research on vaccination rates, and the highest vaccination rate amongst various different belief systems was among atheists.
I did not
Atheists
see
have
that.
the highest vaccination rate in the United States. It's only for the US, but still, there we are.
Wow, I did not see that. You know, in general, I know that I am familiar with certain studies that have shown that people who reject, you know, theological mythologies and religious mythologies tend to replace a lot of that with a hunger for science and knowledge about the way the world really works. They don't take shortcuts of fairy tales and whatnot. All right, speaking of shortcuts, let's talk about the thing in the universe that takes the shortest distance between any 2 points, and that is a ray of light. And I hope that segue was manageable. Joanne is going to illuminate all of us about some of the science, both the history of science and the relevancy of the science of light. So, Joanne, you want to help us all understand better how light fits into our understanding of the universe?
Alrighty, let me do my share screen thing here. And let's see if I can do this now. Do I have everybody up here? Can everyone see this? I hear nods. Am I properly centered? I think I'm going to do that. No, I know it's here somewhere. There it is. There we are. How's that look?
Looks great.
All right. Okay, let there be light. And of course, that's I stole that. That's a famous quote, and it was good. Except, of course, then we separated light from darkness, and I didn't ever figure that one out. Let there be light, and we're going to use it to explore the universe. Now, for many millennia, nobody really figured out what light was. They had no idea. They had no idea what sight was. Some philosophers actually thought that we had beams coming out of our eyes, and that was how we saw. Others say, well, how do you see in a dark room? And on this went. But really, the first guy to ever really look at light at all, in any real sense of the word, was, of course, Isaac Newton. And Isaac Newton he is probably the most famous scientist in the world, even including people like Albert Einstein. He was everything. He studied everything from math to again, light. And in 1666, he began playing with prisms. Now, I'm not quite sure why. He must have been bored, but he was looking at what he called the minimum deviation as a oblong, and that the prism refracts light at different colors at different angles. What he did was this. He had a hole in the wall, the light from the sun shone through, it hit a prism, and the light was displayed on the wall. Now, the round circle was not duplicated. So it wasn't a case of a round light coming through. It became an oblong that was stretched out over space. And they said, wow, look at this. And also, of course, all of the colors. Now, the church just went absolutely crazy about this because, according to the church, the sun was perfect. And the light from the sun was equally perfect, and he had destroyed it. He had done something awful. So, of course, what he did is he took the light from one prism, put it into a different prism, and reconstructed white light, and they were happy. At least they were mollified. But this is the first real investigation into what's light and what is it doing? We jump ahead quite some time, up to 1774, when Frederick Herschel, and again, when it comes to astronomy, Herschel just stands out there as one of the greats. He's the first one to build a really big telescope. He did deep sky surveys. He discovered Uranus as the planet. He proposed the structure of the Milky Way. But for me, the thing that really sets him aside is he discovered infrared radiation. And he was the first guy to use the optical spectrophotometer. And what he did was this. He set up light going through a prism, and the light was sitting down there, reflecting very nicely, and he measured the temperature of all the different lights. He measured the temperature of blue and orange and red, and then he set another thermometer just beyond the red. And it was the hot one. In comparison with all the other parts of light, this is the one that just took off. And he's going, what is going on here? He had no idea, but the idea was there was radiation, there was heat, and he couldn't see it. So this is the first real indication that there is a spectrum of energies far beyond and outside of what we can see, and he could prove it. He could prove that there was actually a different temperature of the different colors of light, and there was a temperature of light that he couldn't see. Now, he looked at the infrared, he looked at the spectrum of many things using his newly found spectroscope, and he saw elements. Now, it wasn't this clear. That is, this is what we see today. He saw elements, and he was transfixed by them. He was very, very excited about what he saw. We jump ahead a few years to one of my favorites, Joseph Fraunhofer, and he invented the modern spectroscope. Now, before that, others had used it, but he really put it together as an instrument. And in the course of his experiments, he discovered bright, fixed lines in the sun. And he looked at these absorption lines. And what he found was, using his really good scientific instrument, the first really good scientific instrument. Now, this, by the way, this particular thing shows a grating. He did not have a grating. He had a prism, a standard old glass prism. And the source was the sun. He bounced it through, refracted it through the prism, and put it onto a wall, and he was able to look. He spread it out over a big, huge distance so that he could see what was going on, and he saw a spectrum. He saw this kind of a spectrum. That is, now, this is a modern one. He didn't see this in anywhere near this detail. However, he did see an incredible thing. We see dark lines in the sun's spectrum. We're looking at it, and we see a place where there is no light. And he went, why? What's going on here? And what we ultimately have concluded is that there are many ways of looking at a light source. One of them is this continuous. Over here on the left, we have a continuous spectrum, and we see this continuous spectrum. This is one way of looking at the sun. A second way, again, we can see this with the absorption lines, which are caused by this cloud of gas. What's happening is the light is coming from the source. It goes through a cloud of gas, and the cloud of gas absorbs light at certain parts of the spectrum. We don't see them because these elements here have taken this particular wavelength of light out. And these are the bright line spectrums. So if we look at the emission spectrum of, let's say, sodium or potassium or calcium, we would see a bright line spectrum. If those elements were in this cloud, they would be removed. We wouldn't see them. There'd be a dark line. And so the dark lines become just as important for us to look at as the bright line spectrum. We can see what elements are in the cloud around the stars. And so a huge and enormous discovery. And again, simple prism mechanisms, and we were able to see these things. And to this day, we can see these things. This particular line here, this D line, this is the sodium D lines, and this is, everyone knows about this. This is sort of the key to looking at something. You look for the D lines because they're just going to stand out. Sodium is ubiquitous throughout the universe. It's really bright. It has a bright orange-red flame. It's a beautiful yellow that just jumps out at you, and you'll always be able to find it. And you can relate everything else. These lines up here, these are oxygen. We get down into here, we've got iron and magnesium and that kind of thing. So again, pretty standard. That is, throughout the entire universe, we can look at any star, we can look at the emission spectrum, we can look at the absorption spectrum and see what elements are actually there. And we can say all the elements that we see here on Earth, they're the same elements that are everywhere in the universe. It's wonderful. I then move on to Festo Slipher, who is virtually unknown. He's the American astronomer who first performed the measurements of the radial velocity of galaxies. That is, when you look at a galaxy, is it just standing still? Is it moving relative to us? And he just one that said, yes, they are moving. They are moving away from us. And he used his spectroscope and observed red shifts. And he said red shifts are related to velocity. And what he did is he looked at this. You notice in the middle, we see our standard spectrum, our absorption spectrum. And right here in the middle, there's our D lines. So we focus in on them. Red shifted. That is, the light is moving away from you. There's the D lines right there. Blue shifted, it's the other way. And he said, all right, what I'm looking at is I'm looking at relative motion. And we think of this in terms of Doppler effect. You know, you have a train that's coming at you and it's, well, if it's coming towards you, the frequency is raised. And so the light would be blue shifted. If it's going away from you, the light is, again, lower frequency, so it's red shifted. And so this indicates that everything is moving away from us at pretty high speeds, actually. And then we come to Edwin Hubble. Again, famous. We know about the Hubble telescope, for instance. Hubble provided evidence that the recessional velocity of a galaxy increases the further it is away. And you go, wait a minute, what does this mean? Well, think of it this way. There are three cars. One of them is traveling away from you at 5 miles an hour. One is traveling at 10, and one is traveling at 20. We'll come back sometimes later. The guy that's only going 5 miles an hour has just gone down the road a little bit. The guy that's doing 10 has gone down quite a ways. The guy that's going 20 is really far away. The further they are away, the faster they're going. And this becomes known as Hubble's law, even though he really wasn't the one who did it. George did it 2 years earlier. So, but the whole idea is that the universe is expanding. And this brought us to Hubble's law. The velocity is equal to Hubble's constant times the distance. So if we know the distance and we know Hubble's law, we know exactly how fast they're going. Well, there's a minor problem with this, and here it is. We don't know what Hubble's constant is. We have two perfectly good methodologies of measuring exactly what it is. For instance, early in the universe's existence, light moved through this plasma. There were no stars. And from the oscillations similar to sound waves, we can deduce Hubble's constant. And we can say that it's about 67 kilometers per second for every 3.26 million light years. Okay. But if we look at it in a different way, if we look at the extreme explosions that are occurring, again, there's a whole series of stars that are exploding, and we know about them, we know what they're doing, and we can actually make a scale and calibrate that scale out. And based upon those values, the Hubble constant is 74. And so this discrepancy is causing all sorts of exciting things happening. We don't really consider this a problem. This is not a problem in science. This is a wonderful opportunity to explore. And boy, are we exploring. We're having a grand time. And everyone is trying to figure out what's going on. Two perfectly good ways of looking at the system, two perfectly valid numbers, neither of which agree. So it's a wonderful area. If anyone is interested in getting into this in the future, the young students, oh, please do. This would be an exciting way. If anyone could actually come up with a solution to this. So, but looking at this, the whole idea was that we could look backwards in time. Using Hubble constant, we could say, where are we now? And look backwards in time to find out where the universe began and how old it is. Well, based upon this idea, we could say that the early universe was really, really small. It was really, really hot and really, really bright, very, very energetic. Now, as the universe expands, what happens? The temperature drops. This is Charles' law. And so these things were very, very high frequencies. The very, very short wavelengths, the wavelengths are going to spread out. They're going to spread out and keep spreading out at lower energies, lower frequencies. The question becomes now, how low? How low is always an interesting question because, again, we're looking at this expanding universe and we're saying, as we go backwards in time from where we are now to the early universe, what has happened to the energy that was right here? Where is it right now? How far has it gone? If we look at the electromagnetic spectrum, we look on the far left here, the far left, really, really short wavelengths, very, very, very high energies. In comparison with the early universe, by the way, these are extremely low energies. These are gamma rays way out here. To give you an idea about gamma rays, if we were to, if a gamma ray burster, let's say 1,000 light years away from here, if a gamma ray burster was directed directly at our planet, our lovely little planet, essentially we would be incinerated. We would be a dead piece of rock floating around the star. It would really just destroy us. So these are enormously powerful, just incredible. As we go down and get lower and lower, the wavelength stretches out, things are getting slower, further and further apart. We get into the realm of X-rays. Now we all know about X-rays. I mean, we go into the hospital, you take an X-ray and it sees right through you. Yeah, and this is light. And we're going, and generally going onto a piece of photographic material or whatever, and we can see right through us. Now, medical X-rays are really, really low energy. They're not high energy X-rays. High energy X-rays would cook you. So we don't do that. Then we slip into the ultraviolet. We know about the ultraviolet also, even though we can't see it. This is the stuff that causes sunburn. And we have sunburn block, and so you put all this stuff on and it stops the UV rays from attacking your skin. But this is really a burn. In between all of this, here is what we see. This tiny, tiny little area. This is all that we see from about 400 nanometers, about 380 nanometers, up through about 750 nanometers. Now, a nanometer. Let's think about this. How big is a nanometer? A meter, you know how big a meter is. It's a little bit bigger than a yard. Cut it into 1,000 pieces. That's a millimeter. It's really small. Cut that into 1,000 pieces. That's a micrometer. Cut that into 1,000 pieces and you have a nanometer. It's really, really, really small. So the wavelengths, the difference between the two peaks in our nanometer scale is really, really close. Moving away further, now we get into the infrared. Yes, the thermometer tells us that it's heat. The thermometer tells us that it's there, but we can't see it, but it's infrared. And we keep on going and going and going. And we get out into the area of microwaves and radio waves and FM radio and AM radio. And we get out into really long waves. These long waves out here are like a meter between the peaks or a kilometer. So these are really far apart. So what has happened in this universe from this really, really small, really excited thing? And it's just blown up over billions of years. How far? And we guessed, we said, you know, we think it's probably in the microwave region. That's most likely it's out there. And so we sent up a satellite to look at the cosmic microwave background. And this is what we saw, a staggering picture. We looked at the temperature of this using microwaves, and we found out that the temperature of the universe is 2.73 degrees Kelvin. Now, the splotchy parts, we get into things like this area here, and this is really, really, really cold. And this is really, really, really hot. And what do I mean by really, really cold and really, really hot? The difference between really, really cold and really, really, really hot is 0.0 0, 0, 0, 6 degrees. There's not much difference. It's cold. And so this actually is a wonderful picture. Can you imagine being able to see 2.73 degrees plus or minus 1, 2, 3, 4, 3? That's an incredibly small number. But it tells us a lot about our universe. One of the things it tells us about it is that our universe is 13.799 billion years old. Billion. Not years, not 1,000 years, not million years, but billions of years old. That's a lot of time. So when we put all of this together, what do we know about the electromagnetic spectrum? Well, we've seen this before. We've seen that it would go all the way from gamma rays all the way out to really, really, really long waves on the order of kilometers or tens of kilometers. That what we actually see is an extremely small part of all this magnetic spectrum. We see a tiny, tiny, tiny little bit. And most of the world, we don't see. We don't see much light at all. And we think that we're pretty good. Well, we are. We're pretty good at what we do, but we miss all of this and we miss all of that. Do we have machines that will work for us to do this? Do we have machines that will see in the ultraviolet and the X-ray and the gamma ray? Yes. Do we see things that are in the radio wave? Yeah. We have FM radio. We have AM radio. We have television. We have radar. We have microwaves that we cook our food in. So can we just see all these things? Yes. Can we use them? Indeed. Do we know about the emission spectra of elements? Yes. We know that each element produces a unique spectrum. And if we want to know what's inside of something, we can use a spectrograph to find out exactly what elements are in there, whether it's sodium or hydrogen or calcium or magnesium. We can see all these different elements. And we know the speed of light. We know exactly how fast it's going. And this is actually an approximation because this can be actually carried out to 2 or 3 decimal points beyond this. So it's really a good number. 299,792, 458 meters per second. That's pretty close. So we know exactly what's, and by the way, we also know that this is the ultimate velocity. This is how fast you can go in this universe. You can't go any faster. And if things are going at that speed, it's called a photon. Which brings us up to, so what? We've done all of this marvelous thing with stars and galaxies, but so what? How does this affect our daily lives? Well, now you're into my bailiwick. I'm a chemist. Now, I'm an analytical chemist, and we ask 2 questions, and we try to answer them. What is it, and how much is there? So let's think about the what is it part. Once again, let's go back to this, and let's think about looking at elements. We can look at a broad spectrum, a continuous spectrum. We can look at a continuous spectrum with the dark lines, and we can look at bright light spectrums. We can use our spectrographs and spectrophotometers for us to actually break everything up and look at things. So I can take a source, and now my laboratories way back when, we actually used a carbon electrode. We would take a solution and put it onto a heated carbon electrode and let the water go off and keep the material. We put this inside and we had a spark source. We let it spark off and it was really, really bright. Now, in our machines, now this tells you how long ago this was, we used a photographic plate, photographic plates to see. That was our detector right here. We had a photographic plate, and we actually looked at how the density of the emulsion and to find out where and how much this was. So we have, of course, improved everything in the past 50 or 60 years, but the basics are still the same. We looked at this and we can see all of the elements. The brighter the light, the more we have. So we can have a quantitative and semi-quantitative. We can also use heat. And this is my bailiwick. This is one of the machines I work with most closely. This is an infrared spectrophotometer. We would have a reference and a sample. The reference, of course, is just it goes right down the tube. There's nothing in there. The sample is sitting in there. And all the light is going through the sample to a mirror. And so we see one beam and then the other beam, one beam and then the other beam, one beam and then the other beam. If the sample absorbs the heat, there's a difference between the two. And our electronics drive themselves to equal it out. And we measure this. We measure the absorption, and we actually put it out on a chart so we can see it. And we have all sorts of help. We've been doing this a long time, so we can actually put this together and say, I know if a band occurs here, if I see something occurs here, I know that it's this kind of a product. I know if it occurs here, it's this kind. We've been doing this a long time. So for instance, if I look at hexane, now this is 6 carbons in a row. So this is just carbon and hydrogen, nothing else, just plain old ordinary hexane. It looks like this. Now, as a chemist, I'm going to look at this and I'm going to study here. This is going to look at this area right up here, around 2900. And I'm going to say, what is that? And I'll look it up and I'll say, all right, so here we are at 2800. I'm going to move up here. And here's the bands that I'm looking at. What are they? These are carbon-hydrogen stretching bands. Carbon and hydrogen, and it's doing this. It's like on a little spring. The hydrogen is moving in and out, closer to and further away from the hydrogen. It causes a dipole moment, and I can see this dipole moment is in the form of an absorption. This is how this thing is normally working. They were not doing anything special to it. This is how this is normally working, and we put the light on it, and the light is simply absorbed because this is what it's doing anyway. Also, I can look at this area right here and say, what's going on here? All right, this is a 1400 again. This is the carbon and hydrogen. The carbon and hydrogen, now we're looking at this motion of the hydrogen moving up and down, flopping around, making a movement. And again, we see a change in the dipole moment, which we can measure as the infrared spectrum. Now let's look at something slightly different. This is the same hexane, but I'm going to put an alcohol right in here. Notice the alcohol is an oxygen with a hydrogen attached to it. And this is in the 3 position here. And now I look and I go, whoa, what's this monster right here? That monster right there is the absorption bands of the oxygen and hydrogen. We're actually seeing that oxygen and hydrogen bopping around. Here's our carbon and hydrogen right here. And more carbon and hydrogen right through here. We say, oh, wow. Now, as a chemist, I can tell you that this is an alcohol. I can tell you that it's an alcohol made up of carbon, hydrogen, and oxygen. I can't tell you which one. I can't see a real difference between the hexane, which is 6, octane, which is 8, decane, which is 10. I can't tell the difference between them because they're all just carbon and hydrogen. I would need some other technique to do that. Now, here is the hexanoic acid, which is the acid form of hexane. Notice we have a double bonded oxygen out here and a hydrogen with an oxygen hanging off of it. A unique setup. And as you'd expect, we see a unique setup in the infrared. Here again, right out here, that's the oxygen and hydrogen. That's the alcohol type thing. But there's a monster right here, right in the middle. This is the carbon and oxygen. This is the double bonded carbon and oxygen, a carbonyl group. And this is a very strong heat absorber. Anytime you have that, it's a really strong heat absorber, just like carbon dioxide. This is carbon dioxide with a chain attached to it. And so we're really absorbing lots and lots and lots of energy right here. Again, I can't tell the difference between one paraffinic acid and another paraffinic acid, but I can say, this is an acid. This is an organic acid. I'm going to go one step further. I'm going to take that acid and I'm going to react it with an alcohol to make an ester. Now notice, we still have this big carbonyl sitting here, this carbon and oxygen thing, but no hydroxyl group out here, no OH. Again, I can turn back to whoever submitted this sample and I say, you've got an ester here. This is some kind of a long chain paraffin, lots of carbons in a row, and somewhere in the middle of somewhere there, you've got an ester going. And what is it? Oh, I don't know. I can't tell you that. The other half of analytical chemistry is how much is there. Now, I can take a spectrophotometer and set up a barrier along the edge here, this is a true physical barrier, and I drive holes into it. And I put a photomultiplier at the other side of that hole. And this is at the specific wavelength of an element. It could be calcium, it could be cobalt, it could be iron. It really doesn't matter. But it's a specific place where one and only one element is going to produce a line. And I burn it right here. It bounces off. In this case, we're using a grating, which is an overgrown prism. And I reflect the light out, and it goes through these little slots. Now, this gives us quantitative information. That is, how much is there? And so this is a huge step forward that I can take to tell not only what's there, but how much is there. I can also use absorption spectra. Remember the absorption spectra? If you put up a cloud in between a source and a detector, I will be able to see that cloud going. Now, in this case, I have a burner, and the burner is about that long, about 4 inches, and I inject a liquid into that burner, and that liquid contains the elements that I'm interested in. Over here, I have a light bulb, and the light bulb is made up of the particular element that I want to analyze. This could be calcium, it could be iron, it could be cobalt. It doesn't matter. I just turn it on, and the light from that, it just shoots out through the flame into the detector, and I measure it. Now, again, this is an absorption technique. The more light that is removed, the higher the concentration. So if no light is removed, there's nothing there. If light is removed, I know there's some of that element there, and I can quantitatively tell you how much is there. How much is that doggy in the window? Can I use light? Ain't light great? Now that we understand it, we can use light to explore the universe. We can use it to explore our world. Without it, we wouldn't see. Oh, by the way, I refer to dark matter because that's one of those things that we can't see. Ta-da! Yay!
Well, that was really excellent. Thank you so much, Joanne. I think that you've really shed light on the universe from our backyard and chemistry labs to the distant galaxies and whatnot. So feel free to stop sharing your screen, and we can get back to just our chatty heads. Yeah. Let me see if I can do more.
Comment on Fraunhofer. He used prisms, but he also used gratings. He made spectroscopes with both kinds of dispersive elements. And the gratings were very important because when you make a grating, you know quantitatively what the pattern is, and you can therefore tell what the wavelength of the light is. Whereas with a prism, you can tell relatively something, but you don't really understand what wavelengths you're looking at, because it depends on the optical properties of the glass that you have to measure somehow, and without a grating, you don't have a way to measure them.
Or in the case of the infrared, it's actually, we use sodium chloride or some other salt. So again, completely different kinds of things, which is always one of the fun parts of working with infrared, is that you're working with salt. So anytime you use water, you dissolve everything. So you can't use water at all.
So Joanne, I have a question. Have you ever, just speaking of some of those old guys, have you ever run across the work of John William Draper? I didn't hear you. I think there's something
Just ring a bell.
Okay, I was just curious, actually, because I wrote about him in my last book, which was called Darwin's Apostles, because he was a big sort of booster of evolution by natural selection back during Darwin's time. And he was an American chemist. And when I was reading sort of summaries of his career given as speeches, late in his life and this kind of thing, a great deal was made of his work in what they called radiant energy. That is to say, light. He was one of those chemists who kind of got into everything. So he looked at, transmission over wires and helped Samuel F.B. Morse figure out the right diameter of wire to use and all kinds of other cool things like this. But he got into, as I said, radiant energy. He looked at electricity passing through filaments and how that could create light. But he also looked at how light affected other things. He got heavily into photography when that was still new, and got into astrophotography as well. So, he kind of, spread himself pretty thin, but was always just, he looked at light from all kinds of different angles. So I was just curious, if you'd ever heard of him.
Not particularly of him, but then again, of course. Now, John, have you ever worked with any portions of the electromagnetic spectrum in your work?
Pretty much all of it.
I thought that question was redundant.
For published papers, they span the sub-millimeter, which is either extreme infrared or extreme radio, depending on who you are, up to the gamma rays. But I've also played around with extremely low frequency radio, not for scientific purposes, but just for fun. And I recently designed a long wave radio interferometer to go in space. And my radio astronomy friends went and simulated it, and they decided it would work, but we couldn't get it funded.
And what would that be used for, John?
A couple things. Part of it was to look at solar flares. And part of it was to look at the portion of the radio universe that you can't look at from the ground because the waves don't get through the ionosphere. And so the idea was we were both going to look inward at the sun and outward at the universe with it. And with guesses of what the galactic plane would look like at those wavelengths, the simulated instrument made a beautiful picture of the Milky Way. But of course, it was just a guess because we've never done it.
Well, keep looking at the scientific instruments that we have that are going out there. We've got, of course, the huge radio waves, antennae that multiple things. We use our entire planet in some of the cases. There's that enormous Auger down in, what is it, Argentina. We have so many satellites out there looking at different portions of the spectrum. And if we didn't know that it existed, of course, we would have no way of looking at these things. The fact that we do, we're exploring everything. And you were talking the other day about looking at, what was it, the electrons in the S level of the, and what was that, a neutron star?
I've certainly talked about looking at electrons from a neutron star. One thing I've worked on is, this is another spectroscopy thing, is cyclotron scattering in the accretion plumes of neutron stars, where you can actually measure the magnetic field by measuring the cyclotron. You see a spectral feature at the cyclotron frequency of the electrons in the magnetic field of the neutron star, and you get numbers that are up into the billions of times the Earth's magnetic field.
One of the
Brings up the interesting problem that Although we can use light to see all of these things and explore the universe and everything else, the one thing we can't do is see dark matter because it doesn't interact with light, at least measurably.
Well, of course, we still use light to probe it because we know about it from measuring velocity distributions of things in space, and noting that the visible matter doesn't have enough gravity to keep things moving around as fast as they are. And of course, how we know how fast things are moving is Doppler. So we do use light to probe dark matter. It's just that we can't see it directly.
Which causes a problem. It's hard to measure something you can't really see.
You know, that reminds me of a thing I find very fascinating, that I've recently been thinking about the fact that we're in kind of a new millennium, and some of the things that have happened technologically, scientifically in the new millennium. And one of the things I've been thinking about is something called multi-messenger astronomy. Now, I may not have my dates exactly correct. I haven't looked this up yet. But I do know for the vast majority of the time, from the time of Galileo looking through a telescope at the moons of Jupiter and the craters on the moon, until very recently, the only way we knew anything about the universe was from light. Maybe a little bit of information from meteorites that people would find on the Earth that had some iron in them and whatnot. But mostly, almost exclusively, we learned about the wider universe from light. And so the study of light, the manipulation of light, breaking light into different colors, understanding what vibrations of molecules make lights. You know, is it vibrations like this? Is it spinning? Is it electrons jumping around within atoms, etc.? Really picking apart the way light works and interacts with matter. Polarization, you know, whether light is emitted in a various polarization frequencies, or linearly polarized or circularly polarized. We have just been able, over 400 years, to really refine the science of using light, just squeezing as much information about nature as is possible, not just humanly possible, but possible anywhere with anybody looking at light anywhere in the universe. We really have a good idea of what light can do and what it can tell us. But within the past 10, 20 years, we've started to be able to get information about the universe from other things. The earliest additional thing was neutrinos. Neutrinos are much more ephemeral than light. They're almost dark matter. They're almost matter that doesn't interact at all, so we could never see them. But they just barely have a little interaction with matter, and using that fact, we can discover things about the sun. In the supernova 1987A that happened in the Large Magellanic Cloud, there was a pulse of neutrinos that was sent out at about the same time that the light explosion happened. And scientists with some of the very first relatively less sensitive neutrino detectors were able to use that burst of neutrinos and triangulate that it happened coincident with that supernova. And then since then, in the past 2 centuries, the neutrino detectors and neutrino telescopes have become a thing. And then finally, the most recent addition, in addition to light and neutrinos, is gravity wave astronomy, which has nothing to do with light inherently. Certainly gravity affects the trajectory of light, and things that emit gravity waves often emit light, etc. But for 400 years, we learned about the universe using the kind of light we can see with our eyes, and then for 100 years after that we used light that we can't see with our eyes, and then recently we've been able to use other radiative phenomena in the universe. So we're getting really good at understanding how to pick apart light, and we're getting better at understanding gravity waves and neutrinos, but there's still more mysteries about those things compared to our really solid understanding of light.
Well, but it's our mastery of light that allows us to do that work, because if you look at the gravity wave detectors, what they do is they are laser interferometers. They are actually using light in extremely sophisticated ways. This is not these are not laser pointers. This is heavy duty stuff to detect the very tiny changes in the geometry of the system that is the detector system due to the passing gravitational waves. And again, the neutrino detectors, you talked about, you were referring to Kamiokande detecting the supernova 1987A. Well, Kamiokande works by first letting the neutrino interact with this big vat of water, which emits an electron, and then they detect the optical flash from the electron. And so again, it's mastery of light. It's a huge collection of photomultiplier tubes in that thing. So, yeah. Oh, Joanne, are you guys still using photomultiplier tubes in spectrophotometers?
Well, you know, it's easier to talk about it as a photomultiplier than it is to talk about other things. Everyone, I think, understands what a photomultiplier is. You know, it's a tube that collects light and explodes.
Yeah, okay.
Are there other kinds of things that do it far more efficiently, far more effectively? Oh yeah.
Because I'm pretty much switched to silicon.
Everything's silicon now. Yeah.
We do have a question in chat. Peter asks, and maybe Ivan, I can direct this to you, give you first dibs on this question. What is the physics of how light is bent? And if photons are passing through dark matter, would the light be bent differently than when passing through non-dark matter? So what do you think about that, Ivan?
Well, I don't think I can explain how light is bent I don't have a simple analogy, I don't think, for explaining that. My sense with dark matter is that it wouldn't directly, I mean, it can change the path of light through general relativity, because dark matter, because it has mass and gravity, means that it's changing the shape of space-time. So it will change the path of light in that way. But when we look at light passing through, let's say, a piece of glass, right? You know, light is hitting this glass and then splitting into multiple colors, right? You can use Maxwell's equations to predict how light is going to pass through this material. And Maxwell's equations, there's one of the parameters that goes into this is how the material, okay, maybe this is the way to think about it. So when you have a photon, it's like an oscillating electric and magnetic field. And as it passes through matter, it's passing through or passing by atoms that have electrons and protons in them. So you have an electric field and you have charges. And so this affects the light in a complicated way. And Maxwell's equations can be used to predict this in a sort of bulk fashion. And you find that light changes direction as a function of its frequency. And that's why the prism is breaking the light into multiple colors.
May I attempt an explanation?
Go right ahead.
Fire ahead, John. Go.
Okay. The glass changes the speed of light. The speed of light that you hear about, this large number, is the speed of light in the vacuum. But when light passes through glass, it slows down. And it slows down at a different rate for different colors. And now if I have can you guys see me? Okay.
The light is really bright on you.
Okay. Oh, it's direct sunlight coming in. Yeah. Well, anyway, if you have a wave coming through the glass, through a medium, and it let's consider the case where the speed of light changes through the medium. It's not quite the same thing, but if the light is slower down here than it is up here, then as the light goes through the medium, the waves bend like this, and they wind up going in a different direction. Now, prism works the same way, except instead of changing the speed of light as you're moving in different places in the medium, it changes the distance that the light has to travel to get in and out, because it's a wedge. And so it's a matter of bending the wave fronts, and the wave fronts bend differently at different wavelengths, at different colors. Does that help?
Yeah, and one thing that I would add to that is the difference with dark matter. So dark matter doesn't have a refractive index. So the bending that John was talking about is associated with a quantity you can ascribe to a material called its refractive index. You can think of it as a measure of by how much that material slows down light. Simple way of thinking of it. Well, dark matter doesn't slow down light. The reason regular matter slows down light is because the light is, you can think of it as hopping between the atoms or the molecules of the material, and it takes it a little while to be absorbed and re-emitted and make the next hop. And that's one of the reasons that material, regular matter in the universe can slow down light. Well, dark matter doesn't absorb nor re-emit light, so it doesn't have the same refractive index property. It doesn't bend or slow light. However, that's not exactly true. You can bend light with dark matter, but it's a completely different phenomena. Dark matter bends the path of light because it has mass, and it's actually the bending of space and the warping of time that Einstein predicted with his theory of gravity that causes the path of light to be deflected by both regular matter and dark matter, independent of any other optical properties. So the same amount of regular matter and the same amount of dark matter, they'll both bend light that travels near them, that grazes near them, by the same amount. But with regular matter, you get to see that material. Literally, you can see it. It's usually made out of stars or glowing gas. And with dark matter, there's nothing to see except the warped path of light that has traveled through or near a dense clumping of dark matter. So it's much, much different in terms of its physical mechanism than the optical properties of something like a prism or a lens.
Yeah,
No, but the same wavefront thing I talked about applies. It's now not that it's moving faster or slower. It's that the wave has farther to go or shorter distance to go because of the warping of space-time.
Cool.
An interesting way to think about it is that Newton said that light or matter, if it's not acted on by an external force, travels in a straight line, or the shortest distance between 2 points. what Einstein did is he really kept this idea that light travels along the shortest distance between 2 points. It's just that the space is now curved. And so it's traveling along the shortest distance between 2 points in a curved space.
Strictly speaking, a curved space-time.
Space-time.
Yeah.
Hi, Mike. Thanks for joining us.
I'm sorry I'm late. I was so overwhelmed trying to sort out a trip to England and Italy and rules and regulations, blah, blah.
Oop. Sounds like you still have some sorting to do.
Yeah, that's something else to do with that.
Joanne gave us a nice overview of the way light is used both nearby for things like chemistry as well as in astronomy. I was wondering if you have a perspective about the way light is used in particle physics. Do you use light, or you just rely on the particles themselves? Is light somehow relevant to the work you do?
It's very relevant in many ways. And let's distinguish between light and photons, because light is a particular wavelength range, right? And so, of course, very short wavelengths is X-rays and then gamma rays. And you can create particles by gamma ray. Is that your dog, Joanne? but also light is used a lot in particle detection in many ways. For example, when a charged particle goes through a medium, like water or glass, because the refractive index of the medium slows light down, but it doesn't slow the particle down. The particle then is traveling faster than light in the medium, and it emits light. It's called Cherenkov light, and it's analogous to the way an airplane traveling faster than the speed of sound emits sound boom, a sonic boom. And that Cherenkov light, which is emitted by a charged particle going faster in the medium, being prompt, can be detected and used. And I built particle detectors using quartz bars to detect the light emitted by these fast particles in photomultipliers or special, very fast photomultipliers to time particles at sort of 10 picosecond level. So light is used a lot in particle detection. But photons of energy in the light region spectrum are too low energy to have a consequence directly on particle physics itself. But when you go to higher and higher energy photons, that's shorter and shorter wavelengths, then the gamma rays can be used to create particles. In fact, my PhD thesis was the creation of particles using a gamma ray beam on a target. And that was back 60 years, well, nearly 50 something years ago. And at the Fermilab Collider and Tevatron, and also at CERN, we use gamma ray collisions to create particles. So 2 photons come in and 2 electrons or 2 muons come out, an effect that we measured at the Tevatron. So it's creating matter particles out of gamma rays. I would say light, but it's really gamma rays. It's very, very high energy light photons. So yeah, I'm sure that there are other ways too that photons are used a lot in particles.
Yeah. Well, the first particle detectors, the Wilson cloud chambers, they used. They had a transparent window that you literally looked through to see the light reflected off of the condensed vapor trail that a particle would leave as it zoomed through the medium.
Right. I was just actually writing about that this week because in this book I'm trying to put together, I was actually photographed looking at a cloud chamber at the Royal Institution when I was a school kid, and it was a little cloud chamber this size. But it was one of the type called a diffusion chamber that didn't have to be expanded, but you had a layer of alcohol vapor and a radioactive source which shoot out alpha particles or electrons or both. And they would make a trail of ions which condensed the alcohol vapor and made a trail of droplets. That's like a cloud chamber, and photograph that. But you could just see them, you could just look there and see these little tracks of particles coming out. And as luck would have it, there was a photographer from the Times newspaper there. I took a picture of me and 3 kids looking at this cloud chamber and published it on the Times newspaper. So that is That's something I'm quite happy that I kept a copy of that picture. So.
That's awesome. Abby, I wanted to pull you into the conversation a little. You talked, I believe, last time or one of our more recent meetings, you talked about how different animals have different sorts of eyes. You talked about spider eyes, for example, and crab eyes and whatnot. What's your perspective about the way different animals use light? Do you have any insight into the differences between different animals and how they use light or what kind of light they use?
Well, I mean, you see lots of different capabilities in the animal kingdom. Squid and other animals like that can see polarized light. I'm not quite sure why, but they do. Various nectar collecting animals like bees can often see ultraviolet light. If you have ever seen photographs of some flowers taken looking at the ultraviolet spectrum, there are a lot of flowers where they basically have a runway for the bees. It's like, here's where you go. So we don't see it. And there are, right here, and there are other things that glow very brightly with ultraviolet light that we can't see. But again, the flowers really look different to those bees. On a more human level, humans, I should actually say that there are some animals that, of course, navigate by light. But on a more human level, we ourselves use light to govern our circadian rhythms. And that's our 24-hour sleep-wake cycles, basically, which are in reality, left to their own devices, more like 24.5 or 25-hour cycles. What happens with us is that our natural sort of day-to-day sleep-wake cycle is more like 24.5 to 25 hours long. If you put people in a cave with no light and no other indicators of time, they will start to desynchronize with the outside world by, again, about a half an hour to an hour a day longer. So if they're in the cave for a month or two, they wind up completely desynchronized in time from the outside world. They think they're getting up at, say, 7 a.m. each morning, but in the absence of clocks, they're getting up at 7 a.m., 7:30, 8, and so on. They just have slightly longer days. This is called free running. And so a lot of work has been done looking into what actually sets our circadian clocks. And humans are very social animals. And so for a long time, it was thought to be social activity or eating or any number of other things. But what actually does it for us is light. Light is what really resets our clocks. What I'm getting at is that because we have this slightly longer than 24-hour natural cycle, it's like a clock that runs a little bit slow that you have to reset every day. And, we have clocks and alarm clocks that do this kind of thing for us. But that is actually not great. It turns out that the thing that really does it for us is light. Light at sunlight levels of brightness, which is far greater than indoor light. If anybody has taken photographs using old-fashioned photography equipment, that sunlight is much, much brighter than indoor light. Our eyes are very good at accommodating to different levels of light. So, you can read indoors with a reading lamp and you think it's perfectly bright. But the reality is that your brain is registering those very low levels of light. So you can read nicely. Our eyes are great at accommodating. Our brains are much less good at accommodating. They know the difference between indoor light and outdoor light. And it is bright levels of outdoor levels, I should say, of bright light that will actually reset your circadian clock for you. And an example of this is, for instance, with jet lag. If you can get a strong burst of light early in your circadian cycle, it'll wake you up. It will tell you that it's morning, that it's time to get going, and the like. So for instance, if you have to be awake and alert at, let's say, about 4 in the morning because you've changed time zones, but normally you'd be asleep at that time, that is enough into that day's circadian cycle that if you're then hit with a bright light, you'll wake up. You'll think it's morning. Your brain will adjust. Your body will adjust. You will get into that new time zone sort of physiologically much more quickly that way. So our actual bodies, our body clocks really are dependent, or at least are most affected, I'll put it that way, by bright light. That's what actually resets our body clocks.
Abigail, that's very interesting. And you're talking about psychological time or biological time at this hourly or daily level. I'm also interested in time at the second level, the very fast level. In other words, how do we know that you, me, and everybody else has the same sense of time at the sub-second level? And for example, I did read somewhere that a tennis champion said that when he's playing tennis in the zone, things seem to slow down. He can see the ball coming in slow motion. He's got time to actually react to it. So that was very interesting. And, people who have to do things very quickly, somehow, do we all have the same sense of time at this fast level, millisecond level, or whatever it is? How do we know that? I don't know.
Well, there tends, you may be talking about two slightly different things. On the one hand, I remember a friend of mine who was a videographer. So he did a lot of work, with TV cameras and the like. And so, when you're shooting TV, you kind of have to, or I should say, they do a lot of short clips. They'll do 10 seconds of this or 30 seconds of that or this kind of thing. And he said that he got very good at estimating to the point of knowing how long, say, 7 seconds of filming was. He had just done it so much that he knew. And I'm willing to believe him. He was a professional. And so he could just, he had done it for so long, he had the chops to be able to estimate seconds. I don't think he could do milliseconds or anything like that, nor did he claim to. But the whole business of things slowing down has a lot more to do with epinephrine. That basically, when we are in this very heightened state of awareness, we are really just much more aware. Visually, things are sharper. Though very often, if sound is not necessary, sound winds up going away. I've had people who were in great peril in sort of the skiing situations that they wished they hadn't been in, and things like this where they were teetering over a cliff or something like that. And they have talked about how everything became exceedingly clear. But on the other hand, a few minutes before, the birds had been singing and various other things were happening. But in that moment of peril, when they were busy trying to get themselves from, falling over a cliff or whatever the case may be, the time really did slow down as they got themselves righted, and their senses of vision and probably of proprioception were very heightened. But on the other hand, man, those birds, they did not hear the birds singing at that moment. So there is a lot that happens with us when we are in these very sort of heightened states of alertness brought on by excitement, by adrenaline. And I'm certain that a tennis champion probably has a lot of epinephrine in their system if they're playing an important match. So this would be my guess.
Yeah, that sounds right. Epinephrine, you said that word. I don't know the word. How do you spell it?
Epinephrine, E-P-I-N, epin, E-P-H-R-I-N-E. Epinephrine, also known as adrenaline. They're the same thing. Sorry, they have two names. They're the same thing.
It reminded me of a very short story by H.G. Wells, famous science fiction writer. H.G. Wells, short story called The New Accelerator. I thought that's an interesting title. So in this story, which was written about 1895, probably, this chemist discovers a drug that makes his brain function speed up enormously, right? It accelerates his thinking, which means that for him, everything else slows down. So he goes outside and he sees people almost not walking, everything is slow motion. And he can run around people and they don't even see him, he's going so fast. And in the end, his clothes start smoking because of friction with the air. And he has to sit down. But it's, H.G. Wells, very clever science fiction writer.
To amplify on some of the stuff that you were just talking about, Abby, they've measured combat pilots, and because much of the stuff is recorded, and they react faster than they're supposed to. As you know, there's supposed to be a time lag between sensing something and then being able to do something about it. And combat pilots are typically about twice as fast as they're supposed to be. They're reacting almost before they can sense it. So the reaction has already occurred. And the fact of blindness, if a combat pilot is focused on another aircraft and they're trying to attack it, there are many, many, many instances where another plane has come between them and they shot their buddy down.
Because they didn't, because they probably didn't see that.
They didn't see them at all, even though it was directly in front of them, directly in their line of sight. And so again, this is how focused you can be. And there are times when you are faster than you're supposed to be biologically. And of course, it's all adrenaline. It's just 100% you're pumped. And when you're coming down off of that, of course, you start shaking.
And you get very tired.
Oh, yes. So when pilots finally land, they're just exhausted. You almost have to help them out of the seat because they're just whipped. They're
wow.
I read recently about an article about great baseball players who apparently they have to start their swing before they could possibly have calculated the motion, seen the ball coming, And so how is that? How does that work? It's almost
a baseball coming at you 100 miles an hour and it's 65 feet 6 inches away from you, and you're supposed to hit it.
And you've already started your swing, so time going backwards, maybe time going backwards.
One of my favorite books about how the brain works is On Intelligence by Jeff Hawkins, and he talks about this, that if you had to calculate the trajectory of the ball, that's a very complicated calculation. So how is it possible that our brains are able to do this calculation? And he says, well, it's not really calculation, it's memory. Right? You remember how it was done, and so you can just initiate the response.
A lot of practice
Without doing the calculation.
I think, again, as basically apes, we're hardwired to it. We can reach out, leap, and grab. And we're good at it. Why? Because that's how all of us started. So we're really good at that. Now, why can we run underneath a ball and the trajectory and just reach up and catch it? Good question. I know I can do it, but hello, Scott.
There's another thing, Abigail, when you're talking about other creatures who have different eyes, bees' eyes, all sorts of different eyes. I remember seeing cartoons of aliens, like little green men, cartoons, because the artists thought they should do something different. They gave them 3 eyes instead of 2.
Why not? Sure.
Why not? But the thing is, they put the 3 eyes sometimes in line.
Right.
Wrong thing, because the middle eye gives you no more information. It should be in a triangle. That gives you more information.
Or one on the back of your head, the way it ought to be,
Or our heads could become massive enough, potentially through evolution, to bend light like a black hole so that we could see things behind us. That would work too.
I think an eye on a stalk would be very handy. So,
Yeah, like snails.
Yeah.
Yeah.
God missed the chance to design us that way.
Yep. Yep.
All right. Well, we are out of time for today. We've had a wonderful discussion about light. And thank you, Joanne, for queuing up that topic and setting us all afire with the enlightening discussion.
Illuminating.
Yes. Next time we'll be back in 2 weeks. It'll be John Doty's turn to pick a deep dive topic, and I look forward to that.
I stole my topic.
Oh, really?
I'm sorry.
What I had started to collect is a bunch of different stuff. So I might just proceed and elaborate on what you did.
Sure. Yeah, there's no harm in that. You know, we've been studying light for hundreds of years as a civilization, so I'm sure.
I skipped the top.
Yeah, it'd be hard to run out of material about it. Thank you all who joined us live on YouTube. We had several viewers today. Thank you to those who are going to show up later. Remember, you can still leave a comment on the YouTube page if you have a question or comment about today's program. Remember to give us a thumbs up, share the word to help us get our program more widely viewed. And thank you very much to our panelists, and especially to Joanne for bringing up this wonderful topic today. Again, everybody stay safe. I hope everybody is vaccinated. Science says it's absolutely the right thing to do, and we all agree. So stay safe, stay vaccinated, get vaccinated if you aren't, and we'll see you again in a couple of weeks.
Joanne, you may have started something. I might do my next deep dive on eyes.
Oh, yes.
Cool.
Great idea. Yes.
All right,
See ya.
bye-bye.